Hello, good evening everybody, and welcome to those of you in the Royal Institution and welcome to those of you online. My name is Ian Chapman. I'm the Chief Executive of the UK Atomic Energy Authority, and we lead the fusion programme here in the UK. I think by definition, if you've joined us either physically or online, you're already interested in fusion. And I think there is huge potential around fusion. Fusion offers the potential of low carbon, sustainable, essentially limitless baseload fuel energy, which can work in all jurisdictions. And that's why we are so excited about it. But we've known that for about 100 years, and these lights are still not powered by fusion energy. So there are still challenges to overcome. Now, if you haven't joined us for the last two seminars in this series, then I do encourage you to watch them, where we talked about the whole point of fusion and the need for it, and then a quick update on where we are in the field. And whilst that potential has been known for a long time, there is a real buzz in our sector right now, real excitement. And that excitement is born from some really, really big advances that have happened over the last really 5 years. So I'll just talk very briefly about 3 big advances. One was from the National Ignition Facility in the US, where we have reached what we call fusion ignition. This is where we get more thermal energy out than we put in to get the fusion reaction started in the first place. And you see that in this graph on the right-hand side, where for about a decade, we were producing a lot less fusion energy than we were putting energy into the system to try to make fusion happen. And then all of a sudden, you see that we got to an ignition, where we got more energy out. And actually, since that happened 2 years ago, they've more or less doubled the power out. So we're continuing to advance and push the boundaries. And I love that plot because it sums up what science is all about. We're trying to do a really, really hard thing here, and for a long time, it felt like we weren't making progress. But it's down to the ingenuity and the brilliance of the researchers that were involved, and frankly, the resilience of the researchers that were involved, to just keep trying and keep trying and keep trying, and eventually they overcame all those challenges. As well as huge progress in the US, there's also been massive progress here in Europe. And this is the largest fusion facility in the world. It's called JET. We operate it here in the UK on behalf of all of our European partners. And last year, we set a new world record for fusion energy produced. This is the only magnetic fusion facility of its scale. It's the only one that can operate with real fusion fuels. The only one with the same mixture of armor that we might use in a power plant. It's just unique. And it is now the world record holder. And those two, genuinely world-first results give us confidence as we move forward with our next step. And this is a big next step that the whole global community are taking together. This is a facility called ITER. It's being built in the south of France. It has 35 countries all working together, essentially most of the industrialized world, 85% of the world's population represented in this project. Yes, you really do have a project where the United States are working with China, and Europe are working with Russia, and also India, South Korea, and Japan as well. So just a hugely, geopolitical experiment as well as a physics experiment. But everybody working together to demonstrate that you can get a very large thermal gain. The idea here is that we put 50 megawatts in to get the fusion happening, and then it will produce 500 megawatts of fusion power out. So this is a really big step, and you can see this is really complicated engineering. Here are components which are about 60 meters in circumference that have to be welded and installed to a few millimeter precision. Incredible, incredible feat of engineering. As well as, so massive physics results that I showed you from NIF and from JET. This huge endeavor of engineering, which shows that we can build power plant scale components in fusion. We also have proper real interest from the industrial sector. Now thousands of companies working in fusion, and investment that we've never seen before. There's now more than $6 billion of investment into private fusion companies, which has just skyrocketed in the last few years. So we have the pull, the imperative to deliver low carbon solutions that the world needs. We have major technical advances, and combining that with a market appetite for investment. So all of those factors make it a really exciting time for fusion. So what we're going to talk about for the next hour or so is what we perceive as the future of fusion. And I'm delighted that with me tonight I have three excellent guests to talk through this. So I'm just going to bring them on now. So firstly, we have Mike Porton, who is the Chief Engineer of Tokamak Energy, the largest fusion company here in the UK. We have Susana Reyes, who's the Vice President for Chamber and Plant Design for Xcimer Energy, an inertial confinement company in the US. And lastly, we have Ahmed Diallo, who is the Program Director of the US Department of Energy's Advanced Research Projects Agency. So, folks, come on up. So the way we're going to run this is that I'm going to ask these folks a few questions, and they're going to come up and answer the question directly to you. I thought I'd start right at the end. So when we have fusion power, who actually wants it? What's the point of it? So we're going to start, who's the user? Who wants to buy fusion? And we're going to work backwards. So let's first of all find a user. Let's assume that we have a user. Then how much are they going to pay for it? How much will it cost that user to buy? So we're going to try and answer that question. Then, before they can buy it, we need to build it. So how are we actually going to build a power station, a power plant? And before you can build a power plant, you have to raise the money to fund the building of it. So how are we going to fund a power plant? Before somebody will give you the money, you first of all have to have a license. You have to have a regulatory regime which allows you to build that power plant. So how are we going to regulate fusion? And then, right at the start, I said to you that whilst fusion has this enormous potential, we still have technical challenges to overcome. So right now, how are we going to innovate? How are we going to invent to overcome some of those technical challenges? So those are the 6 questions we're going to answer over the course of the next half an hour or so. And to start with, I'm going to find out who wants fusion, who will actually use it. And to address that, I'm going to hand to Mike.
Thank you, Ian. Real pleasure to be here with you this evening and with all those online. So, really important question. Everything has to be for a purpose, and exactly who will use this really important outcome. So, very basic to start, we are tapping into that all-important equation that Einstein established of E equals mc squared, relying on nuclear physics to combine typically two light isotopes of hydrogen, converting some of that mass of the resultant resultant products and releasing energy. So we've got an energy product. Now, typically, the way that the field has viewed the likely use of that energy is towards electricity. So taking, in this image, of a prospective magnetic confinement fusion device based on a torus structure of a magnetic cage, coupling that to a grid. And in particular, the typical target we foresee for the application of fusion energy and electricity in particular from it will be either baseload, so that stable provision of electricity production that's the backbone of most electrical grids around the world, or because of the potential to ebb and flow the energy from this system and to control the reacting volume of plasma that comes from driving those isotopes of hydrogen to very high temperatures, to very high energies, it's possible that we could also target peaking. So typically in those hours of the day when there's a surge in demand on the electricity grid, and that puts it into competition with some very different types of energy production and or storage. There are, though, some alternatives. Those include energy production in support of thermal processing and the application of thermal energy intensively to, for example, industries that are very hard to decarbonize. So some target markets for those kinds of energy applications would include running at, say, 100 to 400 degrees to decarbonize the production of paper, or certain refining products, or certain chemical products. It's possible that with fusion devices, if we're ambitious in terms of how high we drive the coolant that harnesses the energy from the system, we could even target things like hydrogen production towards the kind of more ambitious end. Another alternative is to take that nuclear energy that's released from the fusion reaction and actually produce medical radioisotopes. That could be, for example, xenon. It could be the technetium, which is often used for medical imaging, or prospectively, something that fusion neutrons in particular, because they're very high energy at which they're produced, much higher than, say, fission neutrons, it's possible to access different radioisotope products like lutetium, which is being used prospectively in new cancer treatments. The more radical application of fusion energy that has been proposed in some quarters is to prospectively use those high energy neutrons to diminish the legacy activation, the legacy waste from fission-based systems. Much more hard to realize. The combination of fission fuels with this fusion reaction is more difficult, for example, from the perspective of regulation. But there is the prospect that that type of application in the far future could really diminish the stockpiles that result of radioactive waste from fission systems and or the amount of release additional energy from the unused fuel effectively that comes from once through use in things like light water reactors.
Great, thank you, Mike. So, as you can see, there's lots of uses for fusion, not just provision of electricity, but anything from producing paper or helping to treat cancer or producing cement. So loads and loads of potential users for fusion, but nobody will use it if they can't afford it. So how much will it cost? Susana.
Thank you. So what I'm going to show you here in this slide is, in addition to a beautiful picture of what a future fusion plant could look like, and I will talk about this concept later on, here are some results of economic analysis of an nth of a kind type of plant. So this is after we have figured out how the prototypes work and we have a full supply chain in place. So what could be the nth of a kind plant economics could look like? And we have done some analyses that demonstrate that to be competitive, we have to reach a cost of electricity that sits around the $50 per megawatt per megawatt hour, and that's to be competitive enough with other energy sources, including renewables. So what is factored into the calculation of the cost of electricity is going to be the capital cost of building that plant, together with the cost to operate and maintain it, and together with the cost of the fuel. What we have noticed when doing this analysis is that the capital cost of the plant is key, is really dominant. So what is involved in the capital cost is the direct costs of actually constructing the hardware and the indirect costs of financing it, interest rates, etc. So breaking it down in pieces, we look at the direct costs as the maximum contributor, and we can see several cost centers that are the fusion equipment itself, the civil construction, and in the case of laser fusion, the laser cost. So what we are trying to do is find ways to minimize the cost of each of these parts of the hardware. Interestingly, we find opportunities for reducing the cost, such as reusing the power generation equipment from a fossil fuel plant. There are studies that show that if we are able to reduce the electricity generation equipment from retired coal plants, we can significantly save some costs. So other aspects to take into account, as I mentioned, is on top of the capital cost, if we can reduce the time of construction, that's going to reduce the interest rates and escalation. So having short construction terms is very important, and we can achieve that by centralizing production of components that are shipped to several of these construction sites. And finally, a word about operations and maintenance is also a contributor to the cost of electricity. We keep in mind how to make these plants highly available so that the cost of electricity can be cheaper, and efficient maintenance approaches so that these plants can be online for as long as possible. So I'm going to pass it back to Ian now.
Yeah. Thank you. I mean, I can't avoid mentioning, when you talk about a power plant using the infrastructure from a coal power station, to say in the UK we are embarking on a prototype power plant program for fusion, and we have chosen to site that at an old coal station. So it really is fossils to fusion story. Right, so we have a plan for how we might be able to finance it. Now that, of course, will require big leaps in engineering, but can we even build it in the first place? So this is really tough engineering. I think who better to answer that question than a chief engineer? Mike.
Thanks, Ian. building is multifaceted. I'm going to break it down into 3 different parts. First off, it's really important in realizing these systems that we are comfortable with complexity, and also in nurturing the high-tech supply chains that must exist to realize these very, very impressive systems. And none more so than ITER. So the flagship device that Ian alluded to in his introduction, being realized in the south of France at Cadarache, global collaboration, it comprises of about 23,000 technical tons, about 1 million components, 10 million individual parts, and often those individual parts, those components, were without precedence. ITER, therefore, has been a huge success in driving the industrial supply chains necessary for fusion and realizing the types of components on a scale that's consistent with the fusion power plants that follow. And it's also allowed us to bring together, as you can see from this cross-section, the many myriad systems that come together to realize plants on this scale. So that's the physical real estate you need. The other bit around realizing fusion power plants is what goes into them as prospective fuel, and dealing with the bold choices you have to make in the designs and following that all the way through, including all the knock-on effects that come from that. So let's go back to the diagram I showed at the start, which alludes to the DT as the deuterium-tritium interaction that has to happen for most of the fusion approaches that you will see in the public and the private sectors. The 2 isotopes of hydrogen that I hint at are the inputs, deuterium and tritium. Deuterium freely found in nature, for example, in seawater at very low fractions. But tritium, the isotope of hydrogen which has 2 neutrons within it, there are only a few tens of kilograms of it globally. The fusion power plants that we consider from this type of fuel cycle typically will utilize several kilograms per year of operation. Those 2 don't go together. So the choice we're forced with is to realize the tritium fuel that we require inside future fusion power plant devices. So what we envisage is that outside of the center of the fusion reactions taking place, for example, in the cross-section of a tokamak, as the neutrons escape the reaction, they don't see, for example, a magnetic field that might be controlling and shaping the reaction, the neutrons will pass out of the structure into a blanket region, typically containing a lot of lithium, which will allow us, through nuclear interactions between the lithium and the incoming neutron, to produce the tritium that we can feed back into the device and create a sustainable fuel cycle inside the machine. Terrific. Okay, found a solution, in principle. The realities of that include, of course, light bulbs go off in your head, lithium, really useful substance, particularly as we enter a new era of batteries, a new era of EV cars everywhere. That puts fusion in close competition with the emerging supply chains for batteries, of which there have been real spikes in recent prices, something fusion has to wrestle with, has to deal with. But there's an added complexity in that the lithium that we find naturally actually has 2 different components within it, so 2 of these isotopes, slightly different masses of lithium atom within them, one called lithium-6, one called lithium-7. The neutrons that leave the plasma, when they're very high energy, when they first leave the plasma, they love interacting with lithium-7, right? Which is great, because that's the really abundant part of natural lithium that you find. By contrast, as those neutrons slow down in the blanket structure, they have more propensity to interact with the lithium-6. So you're forced with a really difficult design choice now. So you've figured out your fuel cycle. You've decided how you might deal with it by creating a blanket of lithium. You've engineered that very complex structure. But within that, you have to make a choice about the lithium. Do you want to make the lithium-6 more populous? Great idea in principle, drives a whole enrichment process, which is complex, has been precedented. So, for example, a future fusion power plant might need 50 tons of lithium-6 There are precedents for creating about 400 tons of it in previous programs, for example, in the US. But it's an energy-intensive process and also a chemically rich process, which often has some very nasty side effects in terms of propensity for mercury to enter the environment and other things. Not nice. The alternative is you work with the lithium-7 as much as possible, so you just take straight natural lithium. And if you do so, you might have to create some novel structural materials to allow as many of the neutrons as possible to just see that natural lithium and not be lost into the structural materials you box your lithium with. So, as I said, complex design choices. You pick your fuel cycle. You pick how you might work with it. Within that, you have to make some trade-offs, and you might have to figure out extra things beyond it, like how to create the fuels you want, which might not be freely available in nature, might drive some industrial processing that you require, all precedented but difficult. Or you find some novel materials, like, for example, vanadium alloys, which is something that, again, has precedence, but limited scale. And then finally, all important is the human element. People make these machines. Very, very talented, multifaceted individuals, often. And if we are to realize a fusion power plant, for example, in this country, under the auspices of the STEP program that Ian just alluded to, a body that's been brought together called the Fusion Skills Council has predicted that the workforce required will double in the next 5 years and double again in the 5 years beyond. So we're looking at further 6,000 or so highly skilled jobs necessary to realize a power plant in the UK. And those are split across, as you can see, many disciplines, and all the way from kind of extreme qualifications in the postgraduate end down to apprentices. And that's an opportunity as well. Because one of the startling things you find when you start looking at the breakdown of who works in science, technology, engineering, mathematics in the UK, for example, is that less than 1 in 4 STEM employees are female, and less than 1 in 7 class themselves as engineers. So a huge opportunity, therefore, to kind of strike a new balance within STEM subjects, and in doing so, to realize the all-important skilled workforce that must be there to make those all-important difficult design choices, make those technologies real, follow those design choices through to conclusions that make plants real on the scale and complexity typified by ITER.
Thank you, Mike. So you're beginning to get a flavour of some pretty big challenges coming our way. But as well as coming up with some engineering solutions, we need some fiscal solutions. So how are we going to raise what will be many billions of dollars to build every single power plant? Ahmed, some views on that.
Thank you. You've heard about technology challenges. I think we are in a phase where actually we have to think about challenges for investment. And the main one for investing in fusion are government, right? The private sector, that's you and I, we just pay taxes and then we get invested. So, and that started from the beginning at inception of fusion, where we started with research lab that basically put money in it to basically look at a high risk, high reward kind of fusion power plant. Let's not forget, there's also some individual out there, such as tech billionaire as well as venture capitalists, that are willing to invest in fusion. Why? Just simple. They see the potential of fusion emerging. And so far, we have investing about $6 billion from private investment into fusion energy in general. Now, let's think holistically now. Now, governments have funded a little bit for research and development for fusion energy. Now, private investors are seeing, okay, the potential of fusion. Let's merge the two with private-public partnership. And actually, I would add, you can add also philanthropists that are out there. That will merge the three actually in this case, to kind of push fusion energy on the grid as fast as possible. But this is one scheme. But I think we should also think beyond that scheme, that simple scheme, and then look at any emerging technologies. There's always a novel scheme, such a financial model that we can at least create. Can we be more creative in financial models? That could exist. That had happened, for example, in other energy sector in terms of developing new financial schemes, such as green bond, some incentive, for example, of building a power plant. That's another way to provide money into building a fusion power plant. But then last but not least is subsidies. Any emerging, as you know, fusion energy is emerging, but any emerging technology is really, like fusion, would be high capital cost. And in order to kind of facilitate the market entry, you would have subsidies that basically that would help deploy a fusion power plant. But let's not forget, it has to be gradual, a slow subsidy, but that has to pivot around and moving out of the subsidy as soon as possible so that fusion can compete with other energy sector out there. So I think this is what we have in mind right now. That's how I think fusion power plant can be funded and with the $1 billion that are necessary.
Thank you, Ahmed. And of course, we spent more money subsidizing fossil fuels in the last 12 months than we ever have done in the past.
Yes, that's right.
Right, so in order to give those investors, multifaceted range of investors, confidence that we should invest in a fusion power plant, we must have a license. We must be able to regulate it and show that it's safe. So, Susana, some views on how we're going to do that.
This is a very important topic, and I happen to work in safety and licensing for fusion earlier in my career, so I'm very, very enthusiastic about this topic. As you may have heard, fusion has some inherent safety characteristics, and for you to understand the difference with fission, for example, fusion cannot have a runaway chain reaction. If anything, it's the opposite. You may have heard how difficult it is to keep the fusion reaction going. So in the case of laser fusion, that is my field of work, turning off the fusion reaction is as easy as flipping a switch. If anything happens, like we lose power, the fusion reaction stops. If we stop the laser, the fusion reaction stops. If we stop injecting fuel, the fusion reaction stops. So that's why we call fusion an inherently safe source of energy. Now, we have to be transparent and recognize that there are hazards. Michael talked about tritium. Many fusion plant concepts use a deuterium-tritium cycle, and tritium is a radioactive material. And also, the fusion reaction with deuterium and tritium generates neutrons, and the neutrons are going to activate the materials that surround the chamber. So we know that there are hazards, but there are ways, engineering ways, to control these hazards. The same than any radiological facility that you may be more familiar with, like an accelerator or a medical device. Hazards must be controlled. So the good news is that the fuel can be controlled with confinement, right? Not letting it just get out. So we have pipes and vessels that confine the fuel. And the reactivity, the activation of the materials is controlled through shielding to protect the workers and to protect the environment. So, as I said, as any other radiological facility. A word about waste. This is also very important. Another attractive feature of fusion is that our goal is to generate only low activation waste streams, which means that they decay over a short period of time and they can be disposed of via shallow land burial instead of needing deep geological repositories. And some analysis show that after a few years of cooling, materials get to such a low activation level that they can be reused and cleared for going back into other uses in industry. So this is very, very exciting and very important. So based on these characteristics, it's fully recognized that fusion should be regulated very different from fission and with targeted and tailored requirements for controlling the fusion-specific hazards. And this is going to be very important to remove the licensing and regulatory uncertainty when we start deploying these fusion plants so that investors have some certainty of what are the regulatory steps and the requirements to comply with. So the US and the UK, this is very good news. Both the US and the UK have started to think about how to regulate fusion and arrived to a similar conclusion, is that these facilities will be regulated very differently from current fission plants. In the US, for example, we are in the process, the NRC is in the process of modifying the framework that is used to regulate particle accelerators and make fusion a part of that regulation, which is great. It's much more appropriate than fission. And the UK went a step beyond that and said, okay, completely removing from the nuclear regulatory body, and they are going to regulate fusion under the Health and Safety Executive, which is also a full recognition of the very different hazards. So I think this is very exciting for all of us in the field and a very important topic that we all need to keep working on.
Okay, thank you. And last but not least, we still have some big technical challenges to overcome. So how are we going to overcome those technical challenges, the innovation and invention that we need in the next few years? Ahmed, some words on that.
Thank you. Yes, indeed. We still need innovation. This is an important thing that we gotta deal with. And if you think about how we brought fusion up to where we are right now, we relied heavily on collaboration. So meaning public domain researcher worked and collaborating with other researchers across the world. And I like to always actually, now that we're in the UK, if you think about the first major breakthrough in fusion that happened actually in the Soviet Union back then, and it's a scientist from the UK that went to really prove that. And that was a collaboration. Scientists from UK went, measured the electron temperature, that achieved 1 keV, which is like a milestone. And then, after that, the world shifted to one type of concept, that is the tokamak. That, again, need to continue, because we realize that we need to have a broad range of science expertise, as well as mindset thinking about the problem to advance fusion. But let's not forget spin-off. They're the seed. Startup and spin-off also require to be nurtured through that phase. Basically, they have a very small idea. We need to be able to continue helping, when I mean we, I mean the government and the public domain, to continue help them continue through that innovation so they don't fall apart, and continue breakthroughs to advance fusion energy. So those are the innovations. Sorry, I forgot to click, but I think this is, I wanted to kind of think about this. So now we have that frame. Let's imagine, for example, the challenge that we have now. This is a fireplace, and we all enjoy fireplace for millennia. I guess people have looked at it simple. You have log, fire, and a match. Now, this is the simplest way, and a fusion power plant, it's slightly complex, I could say. You can see that's what it is. But there's different elements, Mike alluded to some of them, that we need to start thinking about. So let's go back on the challenges. Go back to the fireplace, what we have. We have the fuel, which is the log here, the match, the fire, and then we have the fireplace that we need to maintain, keep the heat and exhaust the heat. So the first thing I want you to think about, for a fusion power plant, some of us alluded to high neutron flux and high heat. So we can look at the first challenge, which is material. We need to advance material. Material science is the key thing that needs to be advanced. Why? You don't want to have to change your fireplace every 2 days. You want to be having a fireplace that's there for a long time, so you can say, okay, I'm going to start extracting heat out of this, and then put electricity on the grid without having to change to replace the fireplace every few months or so. So that is the first part. The second part is, let's think about the heaters. And we've thought about it. I mean, humankind has been doing this. We improve the matches. You know, we have gas, electric matches now. And so now we have to think about efficient heating system. What does that mean? Really want to make sure that the amount of energy we put in to heat our fuel, here it could be deuterium and tritium, should be really, and compared to the maximum output energy, should be really, really much larger. So we want to minimize any kind of waste heat, waste energy that we use for the heaters. So I think that's crucial. We need innovation to kind of improve the efficiency of the system. Second one is a fuel cycle. We alluded to deuterium and tritium as a fuel. That's what we've been using right now. We want to make sure they're sustainable. That means like we get the tritium, Mike alluded to that, take the tritium, make sure we have enough tritium out there that we don't go and ask for more tritium, so the plant becomes sustainable, and that's really a key goal. But let's also think beyond that. Let's assume we have fusion tomorrow. We need to buy we build like 10,000 plants. That's fine. But we can also think about beyond that. Is there other ways of doing fusion besides deuterium and tritium? The so-called aneutronic, meaning no neutron produced, so that means no damage. That's really thinking this in the future out there. We should have to think about all this. So there are ways to do those fusion type, you need like a better fueling, and we haven't achieved that yet. So we can think about it, that's where innovation comes in. Last but not least is advanced fuel. Advanced fuel in this case is like all the fuel other than deuterium and tritium, but also energy recovery. We have to think beyond just like producing heat out. Can we recover that heat? And there are multiple ways. We can think about the way it's currently done with the turbines, basically heat coming out, and we heat water, and we convert that into electricity. Can we think beyond this? That is, can we get directly the heat converted high efficiency, or with a different fuel cycle, get an ion coming out and directly convert that to electricity? Those are all possibilities out there, and that's innovation. That's all of us here. We should think about it. Now, I don't want to also dismiss other ways. I mean, as you have a power plant, you would need to repair it. So, and in this neutron environment, high heat flux, we need to think about robotic. We need to think about even how to diagnose a power plant so that, we can maximize the output without wasting too much heat. And then lastly and not least is thinking about workforce. Mike alluded to workforce is key. Those people that are basically operating the plant, technician, engineer, everybody, we need to kind of train those, have skill force ahead of that. Now, I would like to kind of switch a little bit. For the material, actually in the US, we launched a new program called Chadwick on material to just very much look at this. Say, can we find, I'm not saying the simple material, can we find this material that can sustain the high heat flux, the neutron in the future? Is it possible? Then we put it out there and we have all the brain, think about it for many years, and hopefully we can achieve something. Thank you.
Thank you, Ahmed. And so, look, some big challenges to overcome, but we've got 3 people here who are trying to overcome those challenges. So I'm really interested in what excites you, right? So you all get, let's say, 6 minutes each to tell me what really excites you about fusion and what's coming in the future. Mike, you go first.
Okay, let's stop 6 minutes. I'll start from a very personal starting point, a bittersweet one. The flagship public programs have nurtured generations of expertise. Ian alluded to the Joint European Torus, operated before I was born in 1983, culminated last year in 2023 in some fantastic world record experiments at the top of a Christmas tree of other facilities that existed in the world, but a landmark that brought through a whole generation of expertise, super important. ITER has driven us to the scale and complexity we need for fusion energy. Okay, terrific, successful, hugely exciting. That is how the public sphere has driven fusion along in the recent past. That has provided a fantastic backdrop to create an industry. It has provided confidence to allow a private industry to be born, one that has, as you can see around the 2000s, exploded into more than 40 companies in the private fusion space. I work for one of those that was founded around 2009 in the shadow of ITER's agreement being signed in 2007. Those are distributed across the world, those 40+ companies. About half of them work on magnetic confinement-based approaches, the other half working on various others, including one of the ones that Susana will showcase in a second. Fascinating, fantastic, hugely exciting when you're in the middle of the field to see these huge public programs creating an entire new industry, bring in that private capital that was alluded to earlier. And I'll give you an example of one of those kinds of stories. So there are 8 companies around the world that have raised more than $200 million in private capital. Tokamak Energy in the UK is one of them, with about $250 million of capital. In the last 10 years, step by step, at pace, wanting to be risk-hungry, so complementing the big, steady, driven public programs which have nurtured expertise and the big programs that have provided the backdrop for fusion, you've got these private enterprises driving on at pace, whether it be world records in the specific devices that we're pursuing. For example, in Tokamak Energy, we go after the spherical tokamak, a very particular style and shape of device that uses magnets to create the bottle, to control the plasma that's at extreme temperatures that makes the fusion reaction happen, or the underlying technologies. In our case, something called HTS magnets, which is a real game changer for fusion. So I've talked macro, now micro. First, a bit of a waymarker. We're now at this really impressive moment where that backdrop of the public programs has been complemented by private money, and we're hybridizing the two. And this is the way that new energy technologies genuinely get born, particularly at the scale when you're realizing a new energy technology and bringing it to the market. And you can see this happening in at least 4 different places around the world at the moment: the Japanese Moonshot program, the German Fusion Forschung program, and then across either sides of the Atlantic, there's a slightly different interpretation of how you bring these public and private hemispheres together to realize the next generation devices that will provide energy to the grid prospectively for the first time. In the US Department of Energy has sponsored 8 startups, maturing organizations, in a kind of runoff for prospective pilot plants designs. In the UK, you've got the STEP program nurtured by the UK Atomic Energy Authority, which is looking to now engage private partners in the next phase of that program to bring their pace and expertise and prospectively scale to complement the public nurturing of the concept. Hugely fascinating from inside the field, and it's how these technologies will be made real. Finally, I'm going to go really small, which is to talk about a specific technology leap. So I've hinted that the magnets are super important for one style of fusion. They create the magnetic bottle that we ebb and flow to control the reacting volume, which is at extreme temperatures. And it's tended to be the magnet technology that has driven the generations of devices. So JET was realized off copper-based coils, so copper-based magnets, the limits of the technology at the time. The ITER device is largely framed around low-temperature superconductors, so superconducting materials. You can provide electrical current through them, and they provide almost no resistance when they're kept to very, very low temperatures, in the ITER case about 4 Kelvin. The next step that we think will unlock power to the grid is something called HTS magnets. High-temperature superconductors, they can run at about 20 Kelvin, so still very cold, and they're based on tape. High-temperature superconducting tape, the magic ingredient in that layered stack that you see on the screen is the REBCO. There are certain material compositions which exhibit this superconducting property. REBCO is one of a family that can be run at these slightly higher temperatures, and we think that will unlock this generation of new devices. Crucially, high-temperature superconductors are really useful in that they can be much more stable than that previous generation, which will allow ITER. They're much more efficient because you only have to cool them to 20 Kelvin instead of 4, so about 5 times saver on the power you consume in the magnets, and ultimately allows us to go to more compact devices, so we'll bring down the scale of fusion power plant devices. That's being made real in fusion right now in the UK at Demo 4 at the Tokamak Energy site in Milton Park, but also across the Atlantic, in an example of a rival company in Commonwealth Fusion Systems, which are realizing their landmark Spark device, which will provide net energy out of the fusion reaction for the first time on a magnetic confinement system. Fascinating times, but also this is an example of fusion transforming industries beyond it. HTS magnets have been made real by fusion companies because of the opportunities we see for it to accelerate that energy technology. But by maturing the supply chains, maturing that technology and its applications, there is the prospect that what we are doing with those magnets can absolutely transform transport. Maglev trains are absolutely possible when you realize it through HTS magnets, to transform medicine, like new NMR systems, and access to analytical science instrumentations, and many more. So one fantastic example of where supporting a technology and a form of energy generation at the absolute cutting edge and high risk, like fusion, can absolutely change society for the better with the applications of spin-off technologies. Over to Susana.
Thank you. So I'm going to now tell you my perspective of what is exciting about fusion, and there are 2 particular things that I'm going to talk about. First of all, as Ian mentioned in his introduction, The National Ignition Facility at Lawrence Livermore Lab in California recently achieved for the first time on Earth in the lab, in a controlled manner, for any type of fusion confinement, we achieved for the first time energy gain, scientific energy gain, which means that we got more energy out of the fuel than the energy deposited in the fuel. And by the way, Tokamak gave a talk recently. If you want to get more details about that, sync to the channel because he has a great talk on that. The other reason to be excited is that Xcimer has a very solid approach to scale up from the science and the same physics demonstrated in the National Ignition Facility up to commercial scale via improvements in the laser technology and innovations in chamber and other technologies. And I'm going to talk a little bit about that. But first of all, a little walk through history. This is the history of inertial confinement fusion research. Many of you have seen Oppenheimer, I guess. You saw the beginnings of the hydrogen bomb. So after that, there was that Atoms for Peace conference where governments decided to do research for peaceful purposes. And people started to look at ways to do fusion in the lab with small quantities of fuel. And in the 60s, the laser was invented, and immediately, scientists at Livermore, led by John Knuckles, is famous for pioneering this field, they started to look about how to use lasers to ignite small amounts of hydrogen fuel. And this is the origins of laser inertial confinement fusion. So scientists at Livermore started building different laser facilities, from one called Janus to Argus, Shiba, Nova. And there were many, many achievements and also many surprises and lessons learned. So throughout all of these decades of research, the basis for the National Ignition Facility was developed. So after NOVA operated in the mid-80s, there was a consensus of the parameters that we would need to build and to operate a laser so that ignition could be achieved. And around the early 90s, there was a decision to build NIF. That was the year that I got into engineering, and actually in the mid-90s, the first time I heard about fusion, I was presented with a slide on NIF and a slide on ITER, and I thought that was really cool. And shortly after, I was doing my master's research in a fusion concept called high life. It was a Livermore concept, and then I was able to go to Livermore to do my PhD research in that same concept and also participate of NIF construction, which was great. After a while, I went, during those years, I also went to ITER to work in safety analysis for magnetic fusion energy, and I was able to participate of the efforts to license the facility in France, ITER. So really exciting. I went back to Livermore at the time that NIF was starting operations in the 2010 year. And, you know, for a while, the scientists at NIF tried really, really hard to get ignition. Actually, I took a break because fusion requires resilience, and there was a point that I got a little bit frustrated, and I went to do other things, but then fast forward to 2022, NIF achieved ignition, and it was remarkable. It was world record, and I decided to get back into laser fusion with my current team at Xcimer Energy. What you can see here is the recent results. The research at NIF has accelerated in the last year. They had a series of successful experiments, so we went from trying really, really hard with, you know, not so great results to really repeating ignition several times in a row. And so basically, we are standing here in the shoulder of giants because you can see all the effort that has been put into this. What we learned from NIF is that hotspot ignition is the way that they achieve fusion gain, works, and that small increases in the laser energy lead to increases in the fuel fusion gain. So this is very important. For those of you that want to learn a little bit of how NIF works, it's basically a laser with 192 beams that are going to deposit a total energy of 2 megajoules in a small pellet inside a can. There's a fusion fuel little sphere inside again, these are called the targets. The targets at NIF are very, very specialized equipment. And the third component that you see here is a chamber. The chamber in NIF is just going to absorb the fusion emissions. It's not meant to recover the thermal power and use it in any way. It's just going to absorb it. This is because NIF is an experimental facility, was never meant to demonstrate commercialization, and also important to know it's an NNSA facility that was mainly, the main mission is stockpile stewardship. Nevertheless, the achievements at this facility have set a clear path for those working in inertial fusion energy about how we can scale this for electricity production. And I'm going to tell you how. So we are working in Xcimer in a new laser concept that instead of glass optics that are used at the NIF, we use nonlinear optics, basically gas. And what are the advantages of using a gas laser is that we are not constrained by fluence on the optics, so we can reach very high energy levels without worrying about damaging very expensive pieces of equipment. And this means that we can achieve energies over 10 megajoules compared to what I said, 2 megajoules at NIF, over 10 megajoules at a lower cost because we don't use expensive optics. So this is very, very attractive. This access to high energies also allows us to conceive very robust targets that are not as specialized as the NIF, very well-pedigreed targets. These targets are much more forgiving, are larger, and not so susceptible to imperfections or defects, so much easier to drive towards ignition than the NIF targets. And finally, the third element I want to talk about here is the chamber. Xcimer is using the high-life concept that I talked about earlier that I started studying during my early career years, and the main advantage of the high-life chamber, it uses a liquid wall to protect all the solid surfaces. So Ahmed talked a little bit about the challenges of finding materials that can withstand the fusion conditions. So with this liquid wall, what we do is we can extend the lifetime of our chamber to the times that we need to operate the plant. And this is very, very exciting. Okay, so it all comes together in this concept. You see a notional picture here of what an Xcimer fusion power plant would look like. Basically, we integrate the laser with the chamber and the targets, and we add a heat extraction system and ultimately a power generation system. So this is a very attractive concept that we are working on. We are in the early stages of coming up with a conceptual design for the pilot plant. Lots of work ahead. We are developing the technology roadmaps to advance the technologies that are now a little bit immature, like tritium breeding, fuel cycle, but really, really exciting. So basically, this opens the possibility of an era with abundant energy for humanity, and this implies that we can access lots of innovations, not being constrained by the use of energy. So we can access innovations in many spaces, from power generation to medical innovations, how we do industrial processes, how we conceive agricultural processes. But in the more mundane day-to-day challenges, I think it's important that we think about how to deploy this energy in a way that it benefits more current socio-economic problems like energy justice. We have to be able to deploy these energy technologies in places that benefit all of the community, not only privileged communities. So very important to keep all in mind as we reach towards the potential of fusion. Ahmed?
Thank you. Well, I think I'm going to try to be brief here, and I would say, first thing for me, what excites me is the legacy of hope and harmony. I'm going to try to explain that a little bit as I go through. Fusion had a promise of abundant energy, carbon-free, clean, equitable. So first thing first, abundance. Why? With the fuel that Mike just alluded to is like deuterium, for example, you can get it from seawater. In principle, we can get, once we know how to breed it, tritium obviously, we can get like abundant energy for everyone. There's no limit. The next big thing we need to think about is try to meet the climate goal. We want to make sure that it's carbon-free. And as you look at a fusion power plant, during the operation, it's totally zero carbon. Okay, that drive is something that we want to make sure we have, and fusion has it, and that's what excites me. So from the get-go, it's carbon-free. There's still some low-level waste that we can get that we try to manage. The next challenge is equity in energy. I think fusion offers something that has never been thought about, is democratizing energy in general. So everyone would have access with abundance, with the carbon-free aspect of it, and sustainability. So those one key aspect, really what drives me, and I think fusion should not just be a dream at that point, but a destination. And that falls into the legacy of hope and harmony. The last is, from me, from a scientist's point of view, is the technology that fusion touches on across all board. Basically, you look at any fusion power plant, you can have scientists from all disciplines that basically work together. And that, to me, is a big challenge to bring everyone together, but also any kind of technology innovation that comes out of fusion could be applied elsewhere. So it's not only for fusion. And I want people to really take that home, because sometimes we get specialized in some specialty, and we don't really get out of the hole and realize that, oh, wait, what I discovered here could be applied in a different field, and have that field advance. And if you think about it, the big hope here has to do with the fact that when fusion was dreamt, was effectively that to take the sun, put it in a bottle effectively, right? Now, if we can achieve that, I think that's a major advancement of prowess for humanity. So that being said, I would say thank you again for this event.
Thank you, Ahmed. What a great summary of the excitement of fusion. Right, we're about to move into questions. I'm going to invite them all to come and sit in front of you, and you can ask any questions that you like. But I'm going to preempt one, because I'm absolutely certain that somebody will say, when will we have fusion? So I'm going to answer it. Fusion will be ready when society needs it. This was said very presciently by one of the inventors of the tokamak, of the basis for magnetic fusion, back in a press conference in the 70s. He was asked, when are we going to have fusion? And he answered it in that way. And I still answer it in exactly the same way. In my view, society needs us. Okay, thank you very much.